Welcome to Science for Sleep, where wonder and calm meet. Each night we drift through galaxies, oceans, and mysteries of the natural world, not to startle, but to soothe. What we will discover by mapping 450 million galaxies. The hidden universe, revealed before the map begins. The universe is vast beyond intuition, beyond memory, beyond the scale that minds evolved on the surface of a single planet can naturally understand. When we look at the night sky, we see only a fraction of what exists. A faint scattering of stars, a quiet shimmer across a dark canvas, familiar enough to feel personal, close, and gentle. But what we see with our eyes is not the universe. It is only the very nearest layer. A thin skin of light resting on an ocean of depths that extend outward in every direction. For every star visible in the night sky, there are many billions more, hidden behind distance, dust, and time itself. And beyond those stars lie galaxies, hundreds of billions of them, each galaxy carrying its own stars, its own worlds, its own ancient structures of dust and dark matter and quiet gravitational tides. The universe is not empty. It is full of patterns, full of motion, full of light that has traveled for billions of years just to arrive here, to be seen for a moment before the human eye closes and night becomes sleep. There is a mission being prepared to make a map of this vastness. A map not of individual stars, nor constellations, nor any one region of the sky, but of hundreds of millions of galaxies. A map of the large-scale structure of the cosmos. A map of the universe as it stretches across time. This mission is called SphereX. Its purpose is not to travel outward into space, but to observe the whole sky from orbit, gathering the faintest traces of light that carry clues about the formation of galaxies, the spread of cosmic inflation, and the quiet evolution of everything that has ever existed. To understand why SphereX matters, we begin with the scale of the universe itself. Light travels quickly, approximately 792 kilometers per second. But distance at the cosmic scale is so immense that even light needs time. When we look at the nearest star beyond our sun, we are seeing light that left that star more than 4 years ago. When we look at the center of our galaxy, we are seeing light that left 26,000 years ago, at a time when early humans were painting animals on cave walls with red and black pigment. And when we look beyond the Milky Way, when we allow our gaze to drift outward across the deep sky, we are seeing light that left its source millions and billions of years before there were human beings, before Earth had oceans, before the sun existed, before stars lit the sky at all. The universe is a record of time carried by light. Every point of light in the darkness is a message from the past. SphereX will listen to those messages, not through sound, but through light that is so faint that it passes unnoticed by the human eye. Light in wavelengths just beyond the visible spectrum, near infrared. These wavelengths slip between dust clouds, travel through the quiet gulf between galaxies, and carry subtle signatures of elements and temperatures and ages. When SphereX observes the sky, it does not simply take images. It collects spectra, tiny fingerprints of light. A spectrum is a story carried in color, even when the color cannot be seen. Every galaxy leaves a trace in the light it emits, how quickly it is moving, how far away it is, how long ago the light began its journey, how much matter surrounds it, how many stars are being born, how many are fading into quiet. SphereX will gather these traces for hundreds of millions of galaxies, and from them, scientists will reconstruct the large-scale architecture of the cosmos. Not just where galaxies are, but how they flow, cluster, stretch, and drift under the influence of gravity and dark energy. Imagine looking not at stars individually, but at the pattern they form across the entire universe. Imagine tracing the filaments of galaxies that run like quiet threads across cosmic darkness. Imagine seeing the empty regions, the dark voids, where almost nothing has formed, where silence stretches across millions of light years with only the faintest traces of dust and gas. Imagine observing the universe not as isolated points, but as a network, a great web of matter and emptiness, like veins of light running through incomprehensible space. This is the view SphereX is designed to make possible. A view of the universe as a whole, a view that is calm, expansive, and quiet. The mission itself is small, as space missions often are. A compact observatory no larger than a refrigerator, built not to impress with its size, but with its clarity of purpose. It will orbit Earth in a gentle rhythm, mapping the sky over and over again, collecting light quietly, steadily, without rush. For 2 years it will sweep the heavens, gathering data not in bursts, but in a slow, continuous flow. A quiet process, like breathing. From Earth, we will watch. Not with urgency, but with patience. Because the universe does not hurry. It does not unfold quickly. It does not demand attention. It simply is. And SphereX will help us see it as it is. No drama, no spectacle, just presence, depth, and scale. The sky is not just above us, it surrounds us completely. It is the ocean we exist inside of. SphereX will map that ocean, and we will drift with it. The shape of the universe. The universe, on its largest scales, is not arranged randomly. It may look scattered when seen with the eye alone, a sprinkling of stars and patches of dark sky without obvious pattern. But when we look deeper, further, and wider, a structure begins to appear. A structure so large that we cannot perceive it directly, because our minds are not built to visualize distances measured in millions of light years. But the structure is there. A quiet web of galaxies stretching across the cosmos. Filaments of matter forming long strands that weave together, meeting at intersections where clusters of galaxies gather like beads of light. And between these filaments are vast open regions called voids. Enormous expanses of nearly empty space where few galaxies formed. Where distance itself seems to stretch unbroken. This web is often called the cosmic web, and it is one of the most beautiful structures known to science. Not because of color or brightness, but because of scale. The filaments are not simply long, they are thousands of times longer than entire galaxies. They are threads of matter spanning hundreds of millions of light years, like rivers of light flowing through darkness. And yet, these rivers move so slowly that their motion cannot be perceived in a human lifetime. They shift over billions of years, guided by the quiet pull of gravity. This structure did not form quickly. It did not appear in an instant. It emerged gradually, beginning from the faintest fluctuations in density in the early universe. When the universe was young, it was dense, hot, and uniform. There were no stars, no galaxies, only a vast glowing cloud of energy and particles. But even in that near uniformity, there were slight differences, small variations. Regions just a little denser than others. Over time, gravity amplified those tiny differences. Matter was drawn inward toward the denser regions, slowly gathering, slowly accumulating, until those regions became structures. And those structures became galaxies. And the galaxies formed clusters, and the clusters formed the web. The pattern we see today is the result of 13.8 billion years of quiet shaping. Not rushed, not forced, just the steady pull of mass upon mass, following the simplest rule that everything attracts everything. The universe is not chaotic. It is patient. Sphere X is designed to observe this web, not directly, the way we might look at a photograph, but through the distribution of light across the entire sky. By measuring how distant galaxies are, how their light has stretched as the universe expands, Sphere X will reconstruct a three-dimensional map of cosmic structure. A map not just of where galaxies are now, but how the universe has grown over time. A map of cosmic history. When we speak of light stretching, we refer to something called redshift. As the universe expands, light traveling through it is stretched, like a wave pulled longer. The more stretched the light is, the farther it has traveled. By measuring redshift, we can understand distance. We can understand age. We can understand motion. Sphere X will measure redshift across the sky with extraordinary sensitivity, allowing us to see the universe not as a flat image, but as a structure with depth. Imagine drifting outward, past the stars of our own Milky Way, past the satellite galaxies that circle it quietly, past the faint distant spirals and ellipticals that reside in the local group, past the boundaries of our galactic neighborhood. Imagine moving into a region where galaxies become points in a much larger pattern, where clusters connect to clusters through luminous threads, where gravity has drawn matter into long, slow arcs of form. This is not movement in space the way walking or flying is movement. It is movement across scales of existence. A shift in perspective so large that ordinary proportions fall away. To think at this scale, we do not measure by kilometers. We measure by light years, by millions of light years, by hundreds of millions, by billions. Distance becomes time, and space becomes history. The galaxies we see are not as they are now. They are as they were when their light began its journey. Some of the galaxies Sphere X will observe are so distant that their light left them before Earth formed, before the sun ignited, before the Milky Way assembled its spiral structure. These galaxies existed when the universe was young, when stars were forming rapidly, when gas clouds were thick and unsettled, when black holes were growing at their fastest rates, when the cosmic web was still tightening into its current shape. To observe distant galaxies is to observe the past directly, not in memory, not in record, but in the light itself. The cosmic web stretches in all directions. Sphere X will not choose one region to study. It will observe the entire sky. A full sky map is rare in astronomy. Most telescopes look deeply in small regions. They trade coverage for detail. Sphere X takes the opposite approach. It sacrifices depth for scope. It sees widely, evenly, quietly. It makes no attempt to interpret. It simply gathers. Every patch of sky, every region of darkness, every faint flicker of distant light. And from that gathering, patterns will emerge. Patterns of clustering, patterns of emptiness, patterns of flow. The universe is vast, but it is not uniform. It has structure, it has shape. Not a shape with edges or boundaries, not a shape like an object we could hold or draw, but a shape formed by the balance between matter, gravity, expansion, and time. Sphere X will reveal that shape, slowly, quietly, continuously. As the telescope passes over the sky again and again, each sweep adds more detail, more clarity, more stability to the map. The universe will not change during this time. The structures being mapped are ancient and steady. The light has already been traveling for billions of years. The map does not need to be quick. It only needs to be patient. In patience, the universe becomes clear, and the night sky becomes not just a backdrop, but a record. A history written in light, waiting to be seen. The first galaxies. Before galaxies existed, the universe was dark, not simply dim, but completely without stars. There was light, yes, but it was the uniform glow of a young universe still filled with heat from its earliest moments. A light without points, a light without form, a smooth, quiet radiance spread evenly across space. This was a time before structure, before shape, before the familiar patterns of spiral arms and clustered stars. The universe was expanding, cooling, and settling. Matter was drifting according to subtle differences in density, responding to gravity so gently that the process is almost impossible to feel. But over millions of years, these tiny differences grew. Dense regions drew in more matter. Sparse regions lost matter. The universe began slowly to develop texture. As matter continued to gather, the first stars ignited. These stars were nothing like the stars we see today. They were enormous, burning hot and bright, short-lived and powerful. They lit the darkness with a light that had never existed before. The first light from the first stars traveled outward, filling space with new illumination. Where before there had been only a uniform glow fading from the early universe's birth, now there were points of light, distinct, bright, and defining. These early stars formed in groups, and those groups became the beginnings of galaxies. A galaxy is not defined by its shape or its color or the number of stars it holds. A galaxy is defined by the simple fact that gravity holds it together. The earliest galaxies were small, modest clusters of stars and gas bound by the gravitational pull of dark matter. They were not stable. They collided. They merged. They stretched and warped. Over time, the collisions built larger galaxies. More stars formed. Gas clouds spiraled inward or were blown outward. The structures we see today, spiral galaxies, elliptical galaxies, dwarf galaxies, are the result of this slow, steady, quiet evolution. Billions of years passed. Galaxies continued to grow. Some became vast spirals with swirling arms reaching outward, each arm a river of stars. Others became spherical or elongated, their stars moving in orbits that no artist could easily draw. Some galaxies remained small, dim, and quiet, like islands of starlight in an ocean of dark matter. Others became bright cities of stars. Each galaxy developed its own history, shaped by gravity, by the gas it held, by the stars it created, by the stars that died within it. Spherex will observe galaxies at many different distances, some nearby, some incredibly far. Because distance in the universe is also time, Spherex will observe galaxies in different eras of cosmic history. Near galaxies show the universe as it is today. Distant galaxies show the universe as it was billions of years ago, when it was young and changing. Even farther galaxies show a time close to the beginning, when everything was new, when stars were forming rapidly, when black holes were growing, when the cosmic web was tightening itself into place. By comparing galaxies across different distances, Spherex will create a kind of timeline. A timeline not written in words or measured on a scale, but visible in the shape and brightness of galaxies across the sky. The universe becomes a story told in light. light that left its source long ago and traveled across expanding space to reach us now. Galaxies do not stand alone. They form groups and clusters. Each cluster contains dozens, hundreds, sometimes thousands of galaxies, all bound together by gravity. These clusters move slowly through the cosmic web, connected to other clusters through long filaments of dark matter and gas. The movement is slow, measured not in years, but in the shifting of millions of years. If we could watch a cluster move, we would not see motion in a moment. We would only see it in time-lapse, across ages. The universe at this scale is calm, not silent, because silence implies the absence of anything, but calm, because everything moves at a pace so slow that it is beyond urgency, beyond reaction. The galaxies drift, not like clouds blown by wind, but like continents shifting, like mountains eroding, like the slow tide of deep time. There are galaxies so large that they contain more than 1 trillion stars. There are galaxies so small that they hold only a few million. Some galaxies are bright and blue, filled with new stars forming from cold gas. Others are dim and red, their stars old and quiet, their gas long since used. Each galaxy carries a memory of how it formed and how it changed. SphereX will gather these memories. It will not decode them directly. It will not interpret. It will simply observe. The interpretation comes later, slowly, through patience and analysis. But the act of gathering is gentle, continuous, unhurried. To map galaxies is to map time. To map time is to understand how the universe became what it is. There is no need for urgency. Galaxies have waited billions of years. They will wait a little longer for us to see them clearly. Light as memory. Light travels freely through space, but space is not always open. There are regions filled with dust, clouds of microscopic grains drifting between stars, remnants of ancient collisions and outflows of dying suns. These clouds do not block all light, but they scatter and absorb certain wavelengths, particularly the ones we can see with our eyes. To us, these regions appear dark, opaque, empty, but they are not empty. They are simply hidden. This is why SphereX observes the universe in near-infrared light. Infrared light is longer in wavelength than visible light. It slips through dust the way a whisper slips through a quiet room. It passes where shorter wavelengths cannot. To the human eye, a region of space thick with dust appears as a blank patch of darkness. But when viewed in infrared, the darkness opens. The dust becomes translucent. The stars behind it emerge. Structures that were invisible suddenly become clear. In this way, infrared light reveals what has been concealed by time and distance. It does not create new information. It simply uncovers what has always been there. SphereX will observe the sky in hundreds of narrow wavelength bands, measuring the exact shade, tone, and spectral signature of the light that reaches it. Each shade contains meaning. A slight shift toward longer wavelengths may indicate that the source of the light is moving away. A faint absorption at a particular wavelength may reveal the presence of a certain element. A gentle slope in the spectrum may suggest the age of stars in a galaxy. Light is not simply brightness, it is information. A single ray of light can contain the history of a star. How hot it is, how old it is, what elements it contains, how its light has been stretched, how far it has traveled, how space has expanded while it moved. This light may have begun its journey billions of years before humans existed. It may have traveled through expanding space, past galaxies that were not yet formed, across distances so vast that the scale defies direct understanding. And yet, it arrives here. Small, faint, quiet, but intact. To study light in this way is to listen to the universe, not as sound, but as memory. Infrared light tells us about the first stars, the formation of galaxies, the growth of black holes, the distribution of dark matter, the rate at which the universe expands. It tells us not only where things are, but how they have changed. When we look at a distant galaxy, we are looking into the past, not a remembered past, a real one. A moment that actually existed long ago. Light does not return. It moves forward, always forward, carrying its origin with it. When SphereX records this light, it is recording time itself, not in seconds or hours or years, but in ages, in the slow, quiet unfolding of cosmic history. The universe does not hurry. Stars form, live, and fade in spans far longer than civilizations. Galaxies drift for billions of years before colliding. Space expands at a rate measured not by motion we can see, but by the stretching of light. To understand the universe, we must match its pace. We must observe slowly, gently, patiently. SphereX will do exactly that. It will look at the entire sky, not once but many times, each pass adding detail, each cycle deepening the map, each repetition clarifying the shape of the universe. There is no rush. The light has already been traveling for billions of years. It will continue to travel. It will wait for us to notice. We do not take this journey by speed. We take it by attention. The universe reveals itself to those who look carefully, quietly, without urgency. SphereX will look in this way, and what it sees will not be noise or confusion or chaos. It will be structure, history, memory, light that has come a long way to be seen. The birth of stars. Stars are not born in open space. They form in regions of darkness. Darkness in the sky does not mean emptiness. It often means concentration, clouds of cold gas and dust, spanning light years in every direction, drifting quietly through the galaxy. These clouds are called nebulae, though the word once meant only cloud before we understood what they truly were. A nebula is not solid. It is tenuous and delicate, so thin that no human hand could touch it, because there is nothing to grasp. And yet, its mass is vast. A nebula can hold enough material to form thousands of stars. It simply holds that material loosely. Over time, gravity works. Not quickly, not forcefully, but steadily. Small regions of the cloud become slightly denser than others. These regions draw in more gas. The more gas they draw, the stronger their gravity becomes. The contraction continues, slowly, like a deep inhalation that takes millions of years. As the gas condenses, it warms. Heat is the signature of motion, particles moving faster as they fall inward, closer together. Deep within the center of this forming sphere of gas, temperature and pressure rise until something profound occurs. Hydrogen fuses. Two hydrogen nuclei combine to form helium. In that moment, light is born. Not reflected light, not borrowed light. Light created from the binding of matter itself. This is the birth of a star. The star glows, not because something burns, but because energy is released in the smallest, most fundamental interaction matter can experience. This light flows outward. And for the first time, the darkness around the forming star is illuminated. A star begins quietly. Its light is soft at first. But as fusion stabilizes, the star becomes steady, constant, self-sustaining. From the outside, the birth of a star seems instantaneous. Something appears where there was nothing. But the process is slow. So slow that if one were to watch without memory or record, nothing would seem to change at all. The universe does not rush creation. It allows things to become themselves over vast and gentle spans of time. When many stars form close together, they create a stellar nursery, a region filled with glowing gas and young stars, still shedding the clouds from which they formed. These regions are some of the most beautiful in the observed universe, though beauty is only a human word for something older than language. Sphere X will not watch stars in the moment of their birth. The time scale is too large. But it will observe the signatures of star formation, the spectral traces in nebulous clouds, the faint glows of gas warmed by the light of newborn stars. It will observe the cycles: gas collapsing into stars, stars radiating light, stars aging and fading, stars returning their material to space. A star does not last forever. Most stars live for billions of years, burning steadily and quietly. But eventually, their fuel depletes. The balance changes. Gravity draws inward once more. The outer layers lift away. What remains depends on the mass of the star. Some stars become quiet embers, white dwarfs. Some collapse into the densest known form of matter, neutron stars. And the most massive collapse further, past the point where even light can escape. Those become black holes. Thus, a black hole is not separate from the process of star formation. It is one possible ending, one path in the long cycle of light and darkness. Stars illuminate the universe. Black holes shape it. These two exist not in opposition, but as parts of the same ongoing exchange. Gas becomes stars. Stars become light. Light travels through the cosmos. Stars fade and return their substance to the nebulae. Nebulae form new stars. A slow breathing, a cosmic inhale and exhale. Far too gradual to sense directly, but written everywhere in the night sky. Sphere X will observe the traces of this breathing, not the motion itself, but the memory of the motion, the record carried in light. The universe changes, but it changes slowly, softly, with patience, just as we move through sleep, gently, one breath at a time. Where light slows. A black hole is not an object in the ordinary sense. It has no surface, no texture, no boundary you could touch or cross in any familiar way. It is a region where gravity is strong enough to prevent light from leaving. To understand how this forms, we return to the life of a massive star. A star is held together by two forces. Gravity pulling inward. Fusion pushing outward. Gravity wants the star to collapse. Fusion wants the star to expand. For most of a star's life, these two forces are balanced. The star shines steadily because the balance is steady. But when a massive star runs out of fuel, fusion weakens. The outward pressure fades. Gravity remains. The core contracts. The collapse accelerates. The matter compresses beyond densities we can imagine. At some point, no known force can resist the collapse. Matter falls inward, not toward a center, but into a state where the concept of center no longer applies. This is how a black hole forms, not as an explosion, but as a quiet, inevitable consequence of gravity. A black hole has a boundary called the event horizon. This is not a wall. It is a threshold. Inside this boundary, the pull of gravity is so strong that light cannot escape. Outside it, light can still leave, though it may struggle. Nothing dramatic happens at the horizon itself. If one could cross it, The crossing would feel no different than drifting deeper into a gravitational well. The change would be subtle. The effects would be understood only later, in time. But time itself is different near a black hole. Not for the one falling in, but for the one observing from afar. To an outside observer, time near the event horizon appears to slow. A clock falling toward a black hole ticks more slowly than a clock far from it. If one were to watch an object fall toward the horizon, the object would seem to approach slowly, slower, slowing further, never quite crossing. This is not an illusion. This is time behaving differently because gravity curves space. Inside the black hole, the concept of time and space exchange meaning. What we call forward in time becomes a direction toward the center. Once crossed, all motion leads inward, not by force, but by the shape of space-time itself. A black hole is a curvature, not an object, a region where geometry bends inward. At the center, mathematics suggests a point known as a singularity, where density becomes infinite, and the known laws of physics no longer describe what occurs. But this is only a symbol for the limits of our understanding. The singularity is not something we see. It is something we infer, a sign that our theories are incomplete. What matters more is how black holes shape the space around them. A black hole does not pull everything into it. Most matter does not fall in. It orbits. Black holes often sit at the centers of galaxies. Our own galaxy has one. A quiet supermassive black hole named Sagittarius A. It is not violent. It does not consume stars constantly. It simply exists, guiding the motion of stars the way gravity always does, gently, continuously. Black holes help galaxies maintain structure. They provide stability at the center. They shape the motion of stars. They are part of the balance. SphereX will not directly observe black holes in visible form, but it will observe the light around them. It will study how stars move in regions where gravity is strong. It will measure the glow of gas heated as it spirals inward. It will read the spectral signatures left behind by matter before it crosses the horizon. Black holes are not the ending of light. They are part of the flow of matter and energy through the universe. Where stars are born from clouds, black holes are born from stars, and the cycle continues. The universe does not distinguish between creation and collapse. Both are motion. Both are change. Both occur over spans too long to feel. The cosmos moves in long, slow arcs. Everything that forms is temporary. Everything that fades is also temporary. Nothing is lost. It simply changes state. The quiet centers of galaxies. At the heart of nearly every large galaxy, including our own, there is a supermassive black hole. These black holes are far larger than those formed from the collapse of individual stars. They hold masses equivalent to millions or even billions of suns. And yet, they are small compared to the galaxies that surround them. The supermassive black hole at the center of the Milky Way, Sagittarius A, contains about 4 million times the mass of the Sun. But the Milky Way contains over 100 billion stars. The black hole is massive, but it is not dominant in size. Its influence is structural, not consuming. It shapes the motion of stars in the core of the galaxy, not by devouring them, but simply by existing. Gravity does not require contact. It does not require motion. It only requires presence. The stars near the center of the Milky Way orbit Sagittarius A in long, graceful curves. Some move slowly, some move quickly, but all follow the geometry of the curved space-time around the black hole. This motion is measured by observing the positions of the stars repeatedly over many years. Their orbits reveal the mass of the unseen center. They trace the shape of gravity itself. A supermassive black hole does not form suddenly. It grows. Over cosmic time, it accumulates mass from, merging with other black holes, drawing in gas from its surroundings, capturing stars that wander too close. But these events are rare on human timescales. For long periods, a supermassive black hole is quiet. Still, unchanging. The space around such a black hole can be calm and stable. The stars in orbit are not in danger. They move as planets move around the sun. Their paths repeat over millions of years. A supermassive black hole becomes a gravitational anchor, a point around which the galaxy organizes. Not all galaxies look the same. Some are spirals with graceful arms of stars sweeping outward. Some are smooth ellipses, rounded and diffuse. Some are irregular, shaped by past collisions. But at the center of many, there is a black hole providing structure, a point of quiet gravity. Spherex will observe the light surrounding these centers, the stars moving around them, the gas warmed by them, the dust shaped by their influence. Not by capturing a single image, but by measuring spectra repeatedly across the sky. The motion of stars near a supermassive black hole carries information about the black hole's mass. The color of the light from stars in that region reveals their age. The faint glow of heated gas reveals whether the black hole is active or dormant. Some black holes are quiet, barely interacting with their surroundings, radiating almost no detectable energy. Others are active. Gas spirals toward them in a wide disk. Friction warms the gas. The gas glows. The glow is bright enough to outshine the galaxy around it. These bright centers are called quasars. A quasar is not the black hole itself. It is the light of matter nearing the event horizon. Matter that is heated by compression, by friction, by falling inward. Light created in the final moments before disappearance. But even this brightness is not violent from the perspective of the gas. The processes are slow. The distances are large. The motion is gradual. From a distance, a quasar appears as a single point of intense light, a beacon from deep time. Spherex will map quasars across the sky. Their distribution reveals how galaxies formed and merged, how the cosmic web evolved, how matter flowed across the universe. By observing many quasars at many distances, Spherex will construct a record of how supermassive black holes grew, not in isolation, but alongside galaxies. As part of the same unfolding structure, galaxies form stars. Stars live and die. Some become black holes. Black holes gather mass. Entire galaxies orbit around them. The universe is not chaotic. It is deeply ordered, not in shape, but in process. A slow, steady, continuous shaping. The center holds, quietly, unseen, but always present. The gathering of galaxies. A single galaxy is vast. It contains stars, planets, clouds of dust and gas, and dark matter forming a quiet halo that extends far beyond what can be seen. But galaxies do not exist alone. They gather into groups, and groups gather into clusters. A galaxy cluster is one of the largest gravitationally bound structures in the universe. It can contain hundreds or thousands of galaxies, each one with billions of stars, all held together by gravity across distances measured in millions of light years. The galaxies in a cluster are not packed closely like stones. There is space between them, vast distances in which entire galaxies could drift without ever colliding. Yet, they remain connected by the shared gravitational field of the cluster as a whole. In the space between these galaxies, there is not emptiness. There is a thin, hot gas, so hot that it emits X-rays. This gas is not dense enough to make a cloud in the ordinary sense. But across millions of light years, its total mass is larger than all the stars in the cluster combined. Even more mass exists in the form of dark matter, an invisible substance that does not emit or reflect light, but whose gravity shapes the cluster's structure. The galaxies move within this unseen framework, like lanterns drifting along the currents of an invisible ocean. The motion of galaxies in a cluster is slow over a human lifetime, but measurable across cosmic time. They orbit the cluster's center, not in circular paths, but in long and gentle arcs. Their motion is guided by gravity alone. Clusters also grow. They grow by merging with other clusters. The mergers occur over billions of years, not abrupt, not violent in the human sense, just the slow interweaving of large structures. When two clusters approach each other, their galaxies pass through one another freely. The space between stars is so large that collisions almost never occur. What interacts more strongly is the hot chaos in the halos of dark matter. The motion reshapes the cluster, forming new patterns of density and flow. Over time, clusters connect to one another through filaments. These filaments contain galaxies, gas, and dark matter stretching across the void. Together, the clusters and filaments form the cosmic web. This structure is not static. It evolves. But the evolution is slow, at a pace defined by the expansion of the universe itself. SphereX will map clusters by measuring the light of the galaxies within them, not by imaging them individually in sharp detail, but by charting their locations across the sky. By measuring redshift, SphereX will determine how far away each galaxy is. By gathering millions of such measurements, it will reveal where clusters are, how large they are, how they are connected. This mapping does not show individual galaxies as shapes. Instead, it reveals the distribution of galaxies, the pattern they create, the structure of space at the largest scale. The cosmic web forms a delicate balance. Gravity pulls matter together. Cosmic expansion pulls matter apart. The result is not collapse and not dispersion, but something in between, a stable structure, a quiet tension. Clusters sit at the nodes of this web, like calm centers where gravity collects matter. Filaments stretch between them like long threads. Voids occupy the spaces between, vast regions with few galaxies. This pattern extends across the observable universe, not in repetition, but in continuity. A single structure without edges, without a center. The galaxies, clusters, and filaments are not arranged with intent. They are shaped by the simplest rule: everything attracts everything. The web is the natural result of gravity acting over time. SphereX will not change the web. It will simply reveal it. Gradually, patiently, as the light arrives. The clusters we will map have existed for billions of years. They will exist for billions more. Their time is longer than the histories of stars, longer than the histories of planets, longer than the histories of civilizations. To observe them is to look at something that endures, quietly, steadily, without needing to be seen. The expansion of space. The universe is not static. Space itself, is expanding. This expansion does not push galaxies through space like objects drifting on a river. Instead, it is the fabric of space that stretches. The distance between galaxies increases because the space between them increases. If two galaxies are very close, gravity holds them together. Their distance remains nearly the same. But if two galaxies are far apart, with great stretches of empty space between them, The expanding fabric of space increases the distance gently and continuously. No force is felt when this happens. There is no sensation of motion, no sound, no wind, just distance increasing. This expansion has been occurring for nearly the entire history of the universe. It began shortly after the universe came into being. At first, the expansion was rapid. Over time, it slowed. Then, billions of years later, something changed. The expansion began to accelerate. This acceleration is gentle, but steady. It means that the universe is not just growing. The rate of growth is increasing. The cause of this acceleration is attributed to something called dark energy. Dark energy is not a force we feel. It is not a substance we can see. It is a property of space itself. As space expands, more space is created. And with that space, more dark energy. The expansion feeds itself. This does not mean galaxies will tear apart. The scale of expansion does not act within galaxies. Gravity within galaxies is strong enough to hold stars together. The planets around stars remain in their orbits. The world remains stable. Expansion acts on scales far larger. Between galaxies, between clusters, across the cosmic web, the expansion stretches the web, not enough to break it, but enough to widen its strands. The light from distant galaxies stretches along with space. Its wavelength becomes longer. We call this redshift. Sphere X is designed to measure redshift precisely. Every galaxy it observes carries the imprint of expansion. The more redshifted the light is, the farther the galaxy is. The farther the galaxy is, the older the light is. By measuring this stretching of light across millions of galaxies, Sphere X will create a map not just of where galaxies are, but of how space itself has changed. A map of expansion. A map of time. This map will allow us to trace how the universe has grown. Slowly at first, then more quickly. Now accelerating. Not as a sudden change, but as a smooth curve across billions of years. The universe does not expand into anything. Space does not need a boundary or container. Space expands within itself. There is no outside, no edge, no center. Every point in space moves away from every other point on large scales. The expansion is even, calm, subtle, unfelt. Yet, over time, the effect is profound. Galaxies that were once near become distant. Light that once traveled easily becomes stretched and faint. The universe grows quieter with distance. Sphere X will listen to that quiet, not by amplifying it, but by allowing it to remain gentle, allowing it to be what it is. The expansion of space is not something to solve or resist. It is simply part of the universe's nature. The cosmos breathes outward, slowly, steadily, without urgency. There is no hurry. There never has been. Before the first light, there was a time when the universe had no stars, no galaxies, and no darkness. Not darkness as we experience it, but the absence of contrast. A time when everything was filled with the same warm, uniform glow. This was the early universe, shortly after its beginning. At that time, the universe was dense, hot, filled with light, and the same in every direction. There were no shapes, no patterns, no clusters or filaments, only a smooth, calm radiance filling all of space. Light existed, but it could not travel far. The universe was filled with charged particles, electrons and protons that scattered light constantly. Light could not move freely. It was absorbed, re-emitted, absorbed again. The universe glowed, but nothing was visible. This period is sometimes called the cosmic fog. Over time, the universe expanded. As it expanded, it cooled. Cooling allowed electrons and protons to combine into neutral atoms. Now, light no longer scattered. It could move freely. It could travel across space without interruption. This was the moment light became visible. Not to eyes, because eyes did not yet exist, but visible in principle. The fog cleared. This light still exists. It travels across the universe today. We detect it as the cosmic microwave background, a faint, uniform glow from every direction. It is the oldest light we can see. Sphere-X will not study the cosmic microwave background directly. Other instruments observe it. But Sphere-X will help us understand what happened next. After the fog cleared, the universe was still smooth, calm, featureless, but not perfectly. There were tiny variations, small differences in density, so small they would be invisible to the eye. These small differences mattered. Where there was slightly more matter, gravity drew more matter in. Where there was slightly less matter, gravity drew matter away. These small variations are the seeds of everything that exists now. Stars, galaxies, clusters, the cosmic web. The universe did not form structure quickly. It took hundreds of millions of years before the first stars ignited. During that time, the universe was dark to any form of light we could see. This era is known as the Cosmic Dark Age, not because light was absent, but because visible light had not yet been created by stars. The universe was quiet, not silent. Silence implies no motion, but quiet in a way that is beyond experience. Matter moved slowly. Gas cooled slowly. Gravity worked patiently. There was no rush, no conflict, only gentle drift. Then gradually, in the densest places, gas collapsed. Gravity strengthened. Temperature increased. The first stars were born. Their light traveled outward across the dark universe, illuminating it for the first time. These first stars were massive, bright, and short-lived. Their light reshaped the surrounding gas, changing the chemistry of the cosmos. When these first stars ended their lives, they scattered the first heavy elements into space. Elements that would eventually become new stars, planets, oceans, mountains, atmospheres, and living beings. The universe became diverse, not uniform, not smooth, structured. Sphere-X will map the traces of this change, not the first stars themselves. They are too distant, their light too faint, but the structures that followed them, the galaxies that grew from those first formations, the clusters that formed from the gathering of galaxies, the web that formed from the long pull of gravity. The universe remembers everything, not in words, not in images, but in the light that has been traveling since the beginning. Sphere-X will listen to that light, quietly, patiently, without hurry, because the universe took its time to become what it is. We take our time to understand it. The gentle mapping of the sky. Sphere-X will orbit the Earth in a slow, steady path. It will not point to a single object or region. Instead, it will sweep its gaze across the entire sky, again and again, in a calm, repeating pattern. Each orbit, the telescope gathers light from a thin strip of sky. On the next orbit, the strip shifts slightly, and over time, the entire sky is covered. Not rushed, not in a single pass, but in a gradual accumulation. Like painting a vast canvas with the smallest possible brush, returning to each region to add depth, clarity, and detail. The observatory sees not with one broad image, but with hundreds of narrow wavelength bands. Each strip of sky is observed many times, in many slightly different colors of infrared light. Where ordinary telescopes see brightness, Spherex sees meaning hidden within the brightness. The temperature of starlight, the age of galaxies, the distance to clusters, the motion of space itself. The data Spherex collects is not a photograph. It is a spectrum, a record of light separated into its component wavelengths. A spectrum is a message. The shape of the spectrum reveals how far the light has traveled, how much the universe expanded while it traveled, what elements the light passed through, how many stars contribute to the glow, whether dust is present, whether gas is warming or cooling. Each patch of sky will be measured not once, but dozens of times during the mission. Repetition is essential. Space observation is not a single moment of clarity. It is a slow refining of understanding, a quiet accumulation, a deepening. The orbit of Spherex is synchronized so that it points away from Earth and the Sun. Its field of view is always turned outward, toward the dark, toward the deep, toward the vast expanse beyond our planet's atmosphere. It moves with Earth, but it looks past Earth. As Spherex continues its scans, the map of the sky becomes sharper and more complete. Not because the telescope changes, but because the data becomes more connected. A single measurement tells very little. 10 measurements begin to form a pattern. 1,000 reveal structure. Patterns in the light become patterns in the universe. Each wavelength becomes a coordinate in time and distance. Each spectral feature becomes a point in the cosmic web. The telescope is small. Its movement is slow. Its observations are gentle. But the scale of what it maps is enormous. This contrast, a small instrument creating a map of an immense universe, is not a contradiction. It is a harmony. The universe does not require force to be understood. It requires patience. Some Spherex will observe bright regions, dim regions, empty regions, crowded regions, regions filled with dust, regions so distant their light is stretched into faint glow. Nothing is prioritized. Nothing is excluded. The map will be complete by design. Over time, the sky will reveal itself as structure, not scatter, as continuity, not isolation, as pattern, not randomness. The telescope does not travel outward to explore space. Space comes to the telescope. The light has already been traveling for billions of years. Spherex simply receives it. Quietly, steadily, the universe arrives on its own time. Why we map the sky. The purpose of mapping the universe is not to find new places to go, not to locate resources, not to reach or claim anything. The map is not for travel, it is for understanding. A map of the sky is a map of how structure forms, how matter organizes itself, how patterns emerge from almost nothing. When we observe the distribution of galaxies, we observe the past written across space. Galaxies are not scattered randomly. Their arrangement contains memory. Memory of the first fluctuations in density, memory of gravity shaping space, memory of stars forming and fading, memory of collisions and mergers, memory of time itself. To map the universe is to read this memory. We learn how galaxies formed by observing how they are arranged. We learn how stars are born by studying the gas that surrounds them. We learn how planets might form by observing how dust behaves in starlight. We learn how life may have emerged by studying where heavy elements appear. The heavy elements, carbon, oxygen, nitrogen, iron, were formed in stars. They were released when stars ended their lives. They drifted into space. They became part of new stars, new planets, and eventually oceans and bodies and breath. When we trace where these elements are, we trace the conditions that allow life to exist. Sphere-X will not look for life directly, but it will map the conditions that make life possible. It will observe the abundance of water-bearing molecules in cold clouds, the chemistry of dust around young stars, the spectral traces of organic compounds drifting between systems. These are the raw materials from which planets form. Not every star will have planets. Not every planet will have oceans. Not every ocean will have life. But the presence of certain molecules in certain environments, in certain quantities, in certain distributions, tells us where the story may begin. Sphere-X will measure these molecules across the entire sky, not in one region, not in one cluster, but everywhere. A global chemical map of the galaxy. It will show where starlight warms dust enough to release water vapor, where cold gas clouds cradle molecules like simple alcohols and carbon chains, where starlight breaks complex molecules apart, where gravity preserves them. This map will reveal where stars are being born now, where stars were born long ago, where planetary systems may form in the future, where the building blocks of oceans are concentrated. The universe is not uniform in chemistry. Some regions are rich in the molecules that support planets and life. Others are quiet and sparse. The map will show the pathways of enrichment, how stars seed their surroundings, how dust carries elements, how gas clouds retain memory. We are part of that memory. The atoms that make up the body, the breath, the heartbeat, the bone, the salt of the blood. All of it once drifted in clouds, lit by newborn stars, long before Earth existed. To map the sky is to trace where we came from, not in a poetic, metaphorical sense, but in a literal, physical way. The universe is not something separate from us. We are made of the same material, formed in the same processes, shaped by the same time. To observe the cosmos is to observe our own origin. Quietly, patiently, without urgency. The map is not a direction outward, it is a reflection inward. The slow evolution of galaxies. Galaxies are not fixed shapes. They change slowly, gently, across billions of years. The form of a galaxy at one moment in time is only a phase of its long existence, a single stage in a slow, continuous unfolding. A spiral galaxy is often depicted as a pinwheel, arms sweeping outward, tracing a graceful curve. But these arms are not solid structures. They are patterns of density. Stars move through them, like waves moving through water. The stars near the center of a galaxy orbit more quickly than those near the edges. This differential motion stretches patterns into spirals. The spiral shape is not forced. It is the natural result of motion persisting over vast spans of time. Some galaxies lose their spiral structure. A collision with another galaxy can soften the pattern. Gravity draws stars into new orbits. Gas clouds shift. A spiral becomes elliptical. This change is not violent in the way we understand violence. Stars do not crash into one another. The space between stars is too large for that. Instead, the motion is smooth. A gentle rearrangement on a scale too large to witness moment to moment. Two galaxies passing through each other is like two patterns of currents meeting in the ocean. The shapes change. The material remains. Over time, galaxies merge. Small galaxies combine to form larger ones. This process is slow. It takes hundreds of millions of years. During the process, stars continue to orbit. Gas clouds continue to drift. New stars may form where gas becomes dense. The galaxy grows, not by construction, but by accumulation. This is how many large galaxies formed, not from a single act of creation, but from the long gathering of smaller systems. There are galaxies that are quiet and old, their stars dim and aged, their gas depleted. They shine with a deep, warm glow, like embers that once were flames. There are galaxies that are young and active, full of blue-white stars forming rapidly. They shine brightly, driven by the energy of new starlight. There are galaxies in transition, neither young nor old, changing slowly as gas flows inward or outward. Sphere-X will observe galaxies across this entire spectrum of ages and states. It will see young galaxies still forming stars, galaxies in midlife, stable and structured, old galaxies where star formation has ceased, merging galaxies slowly combining into new shapes, distant galaxies that show the earliest steps of formation. By observing galaxies at different distances, Sphere-X will observe galaxies at different times. A nearby galaxy shows the present. A distant galaxy shows the past. A very distant galaxy shows the beginning. Layer by layer, the story of galaxy evolution unfolds, not as a sequence of events, but as a continuous, overlapping flow. There is no single moment where a galaxy becomes what it is. It is always becoming, always changing, always moving. The universe does not repeat itself, but it follows gentle patterns. Gravity gathers matter, gas cools, stars form, stars fade, matter returns to gas. The cycle begins again. There is no urgency, no destination, no final shape, only motion guided by time, slow and steady. Sphere-X will not rush to interpret the changes it observes. It will simply record them, patiently, quietly. The understanding will emerge, just as galaxies emerge from clouds of dust, gradually, over time. The unseen structure. There is a form of matter in the universe that cannot be seen. It does not glow. It does not reflect light. It does not absorb light. Light passes through it without interaction. This matter is known as dark matter. The word dark does not mean shadow or blackness or hidden danger. It simply means that it does not interact with light. It is invisible to our eyes and to telescopes that depend on visible light. Yet dark matter shapes the universe. Its presence is known through gravity. Galaxies rotate. Stars in the outer regions of a galaxy move faster than they should if only visible matter were present. If galaxies contained only stars and gas, their outer stars would drift away, slowly, over time. But they do not drift away. They remain in orbit. Something holds them in place. That something is dark matter. Dark matter forms an extended halo around each galaxy, not in a shell or a ring or a boundary, but as a diffuse, gentle field of mass. A galaxy is like a lantern suspended in a vast, invisible structure of gravity. We do not see the structure, we see its effect. The shape of a galaxy is supported by dark matter. The rotation of a galaxy is guided by dark matter. The clustering of galaxies into filaments and webs emerges from dark matter. Dark matter provides the scaffolding upon which visible matter gathers. If we could see dark matter directly, the universe would appear as a network of glowing threads. Great filaments stretching across space, nodes where the filaments intersect, voids between the threads where matter did not gather. Stars, gas, and galaxies trace these threads. Their placement is not random. It follows the structure dark matter created. This structure formed early in the universe, long before stars existed. Gravity caused dark matter to draw itself into patterns. Visible matter followed. The cosmic web, the pattern of galaxies and clusters, is the shape of dark matter, made visible by stars. Sphere X will not detect dark matter directly. No light comes from it. But Sphere X will observe the distribution of galaxies with high precision. From this distribution, the presence of dark matter becomes clear. When many galaxies cluster tightly, there is much dark matter there. When galaxies are sparse, there is less. The map Sphere X creates will show where dark matter is dense, where it is thin, how it flows, how it connects the large-scale structure of the universe. Dark matter does not change quickly. It moves slowly, guided by gravity over billions of years. The web it forms is ancient, stable, enduring. It does not shine, it does not fade, it holds. Everything luminous rests within it. The light of stars, the glow of gas, the arcs of galaxies, all exist because the unseen structure supports them. Dark matter does not speak, but the universe speaks through it. Sphere X listens by mapping the light that responds to it. The visible traces the invisible. The luminous follows the quiet. The seen rests within the unseen. There is no conflict between what we see and what we do not see. They are parts of one structure, one unfolding, one universe. Some things are visible, some things are not, but all are present. The quiet expansion. Alongside dark matter, there is something even more subtle shaping the universe. It is not a substance like gas. It is not a structure like a filament. It is not located anywhere in particular. It is a property of space itself. This is known as dark energy. Dark energy does not pull. It does not gather. It does not bind. It does not form shapes. Instead, it causes space to expand. The expansion of the universe is not an event that happened one time. It is a continuous process. Every moment, space stretches. Distances widen, galaxies drift farther apart. This expansion is gentle. There is no sensation of movement. Nothing rushes outward. No winds of motion sweep through the stars. The galaxies simply become more distant from one another because the space between them slowly grows. Long ago, the expansion was slower. Galaxies moved apart, but gravity still drew matter inward. The balance between expansion and attraction shaped the cosmic web. Then, gradually, expansion began to accelerate. Not suddenly, not sharply, but steadily, softly, in a way that can only be seen when we compare galaxies across great spans of distance and time. The farther away a galaxy is, the more its light is stretched. The stretching of the light shows how much the universe has expanded while that light traveled. Light becomes a record of the expansion. Sphere X will measure this stretching across millions of galaxies. By doing so, it will trace how expansion has changed, not in a moment, but over the entire history of the cosmos. This reveals the influence of dark energy. Dark energy does not interact with matter. It does not respond to gravity. It does not fade or weaken. As space stretches, more space exists, and with it, more dark energy. The expansion feeds itself, but not quickly, not forcefully. The universe expands with patience. In the distant future, clusters of galaxies will remain bound together. Their gravity is strong enough to hold, but the spaces between clusters will widen. The filaments of the cosmic web will stretch. The voids will grow. Light will travel longer distances before reaching any destination. This is not something to fear. It is simply the way the universe moves. No structure lasts forever, but nothing is lost. Everything transforms. Dark energy ensures that the universe does not collapse back into itself. It guides the cosmos outward, making room for time, making room for change. This expansion is quiet. It has no edge, no boundary, no outside. The universe does not expand into anything. It expands within itself, everywhere, equally, calmly. Sphere X will not detect dark energy directly, but it will detect its effect written in light. The acceleration of expansion is inscribed in the redshifts of galaxies. The stretching of wavelengths contains the memory. By mapping this stretching in all directions across the sky, Sphere X will reveal how the universe has opened over time. The expansion is not dramatic. It is steady, soft, continuous, like breath. A slow outward motion that never rushes. Space expands, galaxies drift, light stretches, time unfolds. This is the quiet motion of the universe. Not something to solve, not something to stop, not something to correct, but something to observe, to see clearly, to understand slowly, to accept without urgency. The universe expands, and we expand in understanding with it. The home galaxy. The Milky Way is our home in the universe, not in the sense of place or belonging, but as the structure in which everything we have ever known has occurred. It is a spiral galaxy, with arms of stars and dust curving outward from a central region of greater density. The shape is not fixed. It is the result of motion over billions of years. The stars orbit the center, carrying their light in long, slow paths. Our sun is one of those stars. It is not near the center. It is not near the edge. It lies in one of the galaxy's quieter regions, far from the crowded center, far from the thin outer reaches. This location is calm, stable. The space around the sun is bead and open. There is room for planets to orbit without disturbance. The sun, Earth, and all the planets circle the center of the galaxy once every 230 million years. In all of human history, we have not completed even a small fraction of this orbit. Civilizations rise, grow, change, and fade without moving noticeably along this immense path. Time in the galaxy is measured differently. The stars near the center orbit more quickly. The stars in the outer regions move more slowly. The galaxy rotates, but not like a wheel. It flows, its stars following curved paths shaped by gravity and dark matter. The Milky Way is not alone. It is part of a small cluster of galaxies held together by gravity. We call this the local group. The local group drifts together through a larger region of space filled with clusters and filaments. Beyond the local group, space continues. There are thousands of galaxy clusters extending across the observable universe. But here, within our galaxy, the night sky appears calm. The stars we see at night are only the nearest ones. The galaxy contains hundreds of billions more, too distant to distinguish as individual points of light. Their combined glow forms the soft band across the sky that we call the Milky Way. It is not bright. It is not sharp. It is a gentle haze, the light of countless stars blurred by distance. The galaxy's core lies far away, behind clouds of dust so dense that visible light cannot pass through. But infrared light can. Sphere X will observe the center of the Milky Way in infrared, revealing what dust hides. Cold gas clouds, crowded stars, and the quiet motion of matter near the supermassive black hole. The map of the galaxy will not be a portrait. It will be a record of light, of chemical signatures, of movement through space. It will show where stars are forming now, where they formed long ago, where gas collects, where dust settles, where starlight warms its surroundings. This knowledge does not change the galaxy. It simply allows us to see it clearly. The Milky Way is ancient. It formed from smaller galaxies that merged together, piece by piece, star by star. It continues to change, slowly, gently, without haste. Our sun will circle the galaxy many times before it fades. The planets will drift with it. The stars will shift in patterns too slow to witness directly. But the shape of the galaxy will remain. Spiral arms will continue to curve. The core will continue to shine. The halo of dark matter will continue to hold. We live in a single small moment of a vast structure. A moment quiet enough for thought, calm enough for observation, still enough for reflection. Spherex will observe the galaxy from above the atmosphere in the silence of orbit, where nothing interferes with the light that arrives. The galaxy does not announce itself. It does not call attention, but it is always present, surrounding us completely. We are inside it. We always have been. We always will be. The shape of time. Time in the universe does not move as we experience it. We measure time in hours, days, and years. We watch moments pass. We feel change as something immediate, something noticeable. But cosmic time is different. It unfolds slowly, patiently, across spans longer than memory, longer than history, longer than life. A star lives for billions of years. Its birth is not a sudden moment. It begins as a cloud of gas, drifting quietly in space. The cloud gathers, grows denser, warms from the inside. Slowly, over millions of years, a star ignites. The light from that ignition travels outward, crossing the space around it, moving through the galaxy, continuing long after the star has faded. Galaxies evolve even more slowly. Their shapes change over hundreds of millions of years. Their arms reshape. Their centers shift. Their stars drift in orbit. The motion is too gradual for any observer to notice in a single lifetime. Cosmic time is not rushed. It has no urgency. There is no need to arrive anywhere at any particular moment. The universe simply continues. Even its beginning was not a single explosion, but a slow cooling, energy spreading, light stretching, space widening. The early universe was smooth. Over time, it developed structure. The structure grew in complexity. Stars formed, galaxies formed, clusters formed, webs of matter extended across the cosmos. Each of these steps took millions or billions of years. In cosmic time, change is steady, continuous, unaffected by haste or delay. Spherex observes the universe as a record of time. Light from distant galaxies left them billions of years ago. To see them is to see the past. Light from nearby stars left them only moments ago. To see them is to see the present. The sky is not a single moment. It is many layers of time overlapping. Every region of space we observe shows a different chapter of the universe's history. Spherex will assemble these layers, not into a linear timeline, but into a map of time woven through space. A cosmic timeline that does not move forward, but outward. The farther we look, the older the light. The farther the light has traveled, the longer space has been expanding while it traveled. Time becomes distance. Distance becomes memory. Memory becomes structure. The present moment is only one point on a long, gentle arc of time. Stars will continue to be born. Galaxies will continue to drift. Light will continue to travel. Space will continue to expand. None of this requires attention. None of it requires intervention. It simply unfolds. Our experience is brief. But within that brief moment, we have the opportunity to observe. Not to change the universe, not to direct it, but to understand that we are part of it. Not separate, not outside, not spectators. We are made of the same matter that stars formed from, carried across cosmic time to this moment. Cosmic time is not distant. It is within us. The breath, the heartbeat, the presence, each is part of the same unfolding. Sphere X observes time not as a clock, but as light traveling through space. Time that has traveled billions of years to arrive gently in the quiet of an orbiting telescope. Time arriving softly. The life of stars. Stars are not eternal. They have beginnings, they have lives, they have endings. But these processes unfold so slowly that they feel timeless. A star begins far from brightness. It begins in cold, quiet clouds of gas and dust. These clouds drift in the darkness of space, undisturbed for millions of years. There is no light there, no heat, only stillness. Over time, gravity draws the gas inward. Not quickly, not abruptly, just slowly, with patience. The cloud contracts. Its center becomes dense. Pressure builds. Temperature rises. This continues for a long time until the core becomes hot enough for fusion to begin. Hydrogen atoms combine into helium. The reaction releases light. The star shines. This is the quiet beginning of starlight. A star does not burn. It glows from within. Its radiance is steady, unhurried, continuous. The balance between gravity pulling inward and fusion pushing outward creates equilibrium. This equilibrium lasts for millions or billions of years. During that time, the star provides warmth to any planets around it. It shapes the motion of dust and gas within its system. It illuminates its surroundings. Stars differ in size and brightness. Some are massive and blue-white, burning fuel quickly, shining intensely, living briefly. Some are small and red, using fuel slowly, shining softly, living for trillions of years. Our sun is in between. Warm, steady, long-lived. A stable star in a quiet region of the galaxy. As a star ages, the balance changes. Hydrogen in the core grows scarce. Fusion shifts. The core contracts. The outer layers expand. The star becomes a red giant. Not suddenly, but slowly, over millions of years. For some stars, this is the final form. They shed their outer layers gently, releasing gas into space, creating clouds of color and light that drift for ages. The core remains behind as a white dwarf, a small, dense remnant cooling slowly, very slowly, over billions of years. Other stars are more massive. Their endings are different. Their cores collapse. Their outer layers are hurled outward in a supernova. This is not an explosion in the violent sense we imagine. It is a release, matter returning to space. This matter contains heavy elements: carbon, oxygen, nitrogen, iron, created within the star over its lifetime. These elements spread into the galaxy. They join gas clouds. They become part of new stars, new planets, new oceans, new forms of life. Every atom in every breath has traveled through this cycle. We carry the memory of stars in the structure of the body. Sphere X will observe the clouds where stars are forming now. It will see cold gas collapsing. It will see dust warmed by newborn light. It will detect the spectral traces of molecules that gather before stars exist. By mapping these regions across the galaxy, Sphere X will show where the next generation of stars will form. Not in a single place, not in a single moment, but throughout space, always, continuously. The universe is not finished. It is still forming, still shining, still unfolding. Stars begin, stars fade. Matter returns to clouds. The cycle continues. The life of stars. Stars are among the most influential structures in the universe. They shape galaxies. They create the elements that form planets. They produce the light that travels across space for billions of years. They provide energy that can allow chemistry to become biology. They are not simply points of light in the night sky. They are long, slow processes of matter, temperature, and gravity unfolding across cosmic time. Every star begins in a place that does not shine. In regions of the galaxy where starlight does not easily reach, there are giant molecular clouds, vast accumulations of cold cumulus and interstellar dust. These clouds can stretch for dozens of light years. Their temperatures are extremely low, sometimes only 10 to 20 degrees above absolute zero. At these temperatures, atoms move slowly. The gas is calm. The dust settles into complex filaments and layered shapes. These regions are quiet, but not motionless. Gravity is always present. Very slowly, over millions of years, gravity draws parts of the cloud inward. Not as a collapse in the way we understand falling, but as a gentle gathering, density increasing gradually, as though the cloud is simply remembering where it wishes to be. The process begins when the cloud becomes slightly denser in one location than another. This density can be caused by many things. A shock wave from a distant supernova, the passing wave of a spiral arm, or subtle changes in motion within the cloud itself. Once a region becomes denser, gravity strengthens there. That region grows denser still. The process continues. Over time, the densest region becomes a protostar, a forming star still hidden within a thick cocoon of dust. This stage is not bright to the eye, but it is warm compared to its surroundings. The dust around the protostar absorbs this warmth and re-emits it as gentle infrared radiation. This is where instruments like spherex are useful. Infrared light passes through dust more easily than visible light. So while optical telescopes see darkness in these regions, an infrared survey reveals the quiet beginnings of starlight. Inside the protostar, the gas continues to collapse. Pressure increases. The temperature in the core rises. Eventually, after millions of years of contraction, the core becomes hot enough for nuclear fusion. Fusion is not combustion. It is not fire. It is the merging of atoms under immense pressure. At the core of a star, hydrogen atoms move so quickly and collide so forcefully that they combine to form helium. This process releases energy in the form of light. The light pushes outward, balancing gravity's inward pull. A star begins its long, steady phase of life. This phase is called the main sequence. Our sun is currently in this stage. It will remain here for billions of years. During this time, the star is stable. Its temperature is steady. Its brightness is predictable. The fusion reactions in the core produce a constant outward pressure that balances the star's own gravity. The size and temperature of a star depend on its mass. Stars that are much more massive than the sun are hot, bright, and blue-white in color. They shine intensely and use their hydrogen fuel quickly. They may live only a few million years. Stars that are less massive than the sun are cooler and red in color. These red dwarf stars burn their fuel slowly. They can shine for trillions of years, longer than the current age of the universe. This means that, in cosmic terms, the universe has not yet seen even one full life cycle of the smallest stars. They are still in their youth. Their futures extend far beyond the present time. While a star shines, it shapes its surroundings. The light and heat it emits influence nearby dust and gas. This energy can create regions of warm plasma, forming structures called H2 regions, large glowing clouds where young stars illuminate hydrogen gas. These regions are not static. They expand slowly. They interact with surrounding molecular clouds. They may trigger new waves of star formation. The life of one star can lead to the beginning of others. Meanwhile, planets begin to form around young stars. They begin as disks of gas and dust that orbit the star, flattened into a thin plane by the motion of rotation. Dust grains within the disk collide and stick together. These grains become pebbles. Pebbles become stones. Stones become planetesimals. And over long periods of time, planetesimals gather into planets. This process can take tens of millions of years. There is no acceleration, no sudden jumps, only gradual accumulation guided by gravity and motion. Life on planets, if it emerges, does so much later. Stars remain stable for the majority of their lifetimes. But eventually, the balance changes. The hydrogen in the core becomes depleted. Fusion slows. Gravity begins to draw the core inward again. The star responds by expanding. Its outer layers swell outward, becoming cooler and redder. The star becomes a red giant. This stage can last hundreds of millions of years, depending on the star's mass. For a star like the Sun, the red giant phase will end when the outer layers drift away into space, forming a planetary nebula. A faint, expanding shell of gas lit by the remaining core. The core itself becomes a white dwarf, a dense, hot object roughly the size of Earth, but with the mass of a star. A white dwarf no longer undergoes fusion. It simply cools, slowly, over billions of years. Massive stars end differently. Their cores become heavy with elements like carbon, oxygen, and iron. When the core can no longer support its own gravity, it collapses rapidly. This collapse triggers a supernova, an outward release of energy that can briefly outshine entire galaxies. The material expelled into space contains heavy elements that only stars of great mass can form. These elements drift through the galaxy and become part of new molecular clouds. New stars, new planets, new oceans, new forms. The atoms in our bodies came from stars that lived and died long before the Earth existed. Carbon in our cells, calcium in our bones, iron in our blood, all formed in the cores of ancient stars. So when we observe starlight, we are observing the story of matter's journey from cloud to star to space to life. SphereX will study these processes across the galaxy. It will observe molecular clouds where stars are forming now. It will measure the distribution of dust heated by young stars. It will detect the spectral signatures of ices, carbon compounds, and silicate grains. It will help identify how widespread the conditions for planet formation are, not through a single observation, but through a survey of the entire sky. The life of stars is not a set of stages to memorize. It is a cycle, continuous, unbroken, happening everywhere at once. Billions of stars at every possible stage spread across the galaxy and beyond. The universe is full of starlight, soft, steady, enduring. Everything we see, everything we touch, every moment we experience is shaped by the long life of stars, and the cycle continues. The formation of planets. The formation of planets does not begin with worlds, or surfaces, or oceans. It begins with something small: dust, gas, and motion. Around every young star, there is a protoplanetary disk. This disk forms naturally from the collapse of a molecular cloud. As the cloud contracts, it begins to spin. The rotation flattens the remaining gas and dust into a disk that orbits the newborn star. The star shines at the center. The disk surrounds it like a ring of potential. The material in the disk is not smooth. It contains tiny grains of carbon, silicates, ice, and metals. Most grains are far smaller than the width of a human hair. Yet they are the beginning of everything that will one day become solid worlds. The temperature in the disk varies with distance from the star. Closer in, the disk is warm. Farther out, it is cold. This temperature difference determines what materials can exist in solid form. In the warm inner regions, metals and silicates remain solid. Water, carbon dioxide, methane, and other volatile molecules exist only as gas. Planets forming here tend to be rocky, dense, and compact. In the cold outer regions, water and carbon compounds condense into ice. Icy grains are more sticky than silicate dust. They combine more easily. This allows planets forming in the outer disk to become large and massive, gas giants or ice giants. Thus, the architecture of a planetary system begins with temperature, distance, and the behavior of dust. The first step: dust to pebbles. Dust grains in the disk collide gently. The collisions are slow because everything shares the same orbital motion. The grains stick together through weak forces, electrostatic attraction, surface bonding, and the geometry of rough surfaces. Over many thousands of years, dust becomes clusters. Clusters become grains. Grains become pebbles, objects only centimeters or inches wide. This is the first stage of growth, and it happens quietly. There is no sudden change, no spark, no event to mark the transition, just accumulation. Pebbles to planetesimals. Pebbles continue to grow, but now something new begins to matter. Gravity. Once an object reaches a size of about a meter, its gravity is enough to influence nearby material. It does not pull strongly, but it gathers dust and pebbles faster than they collide randomly. This stage is a threshold. Once reached, growth accelerates. Some regions of the disk become dense enough for streaming instabilities, a process where pebbles clump under their own motion and gravity. These clumps collapse into planetesimals, solid bodies ranging from kilometers to hundreds of kilometers across. Planetesimals are the first objects large enough to be considered building blocks of planets. They have surfaces. They cast shadows. They move through the disk as individuals. Their creation is slow. But once they exist, the pace of planet formation changes. Planetesimals to protoplanets. Planetesimals collide and merge. Some are shattered apart. Others gradually accumulate more mass. Gravity guides these interactions, quietly, steadily. Over millions of years, the largest planetesimals grow into protoplanets, bodies that are hundreds or thousands of kilometers wide. Their shapes become rounded by gravity. Their interiors begin to differentiate. Heavy elements sink toward the center. Lighter material rises outward. A rocky world is taking form. In the inner disk, protoplanets will eventually become rocky planets, like Earth, Mars, and Venus. In the outer disk, protoplanets may grow large enough to capture massive envelopes of gas, becoming giant planets like Jupiter or Saturn. The formation of planets is not uniform. It does not follow a single pathway. The outcomes depend on mass available, distance from the star, temperature of the disk, chemical composition, time available before the disk dissipates. Every planetary system becomes its own unique arrangement. No two are alike. The role of gas plays an essential role in shaping planets, even those that do not retain gas atmospheres. As planets move through the disk, they interact with gas. The gas pulls slightly on their orbits, causing planets to migrate inward or outward. Migration is slow, but significant. A planet may form far from its star and drift closer over millions of years. This is how we believe hot Jupiters, large gas giants extremely close to their stars, may have formed. Migration shapes the final layout of a planetary system. Planets do not always remain where they were born. They travel through the disk, influencing each other, exchanging momentum, carving gaps, clearing paths. This process determines whether a system develops. Compact rocky planets, widely spaced worlds, chains of resonant orbits, or solitary planets in wide, quiet arcs. The variations are almost limitless. The end of the disk. Eventually, the protoplanetary disk thins. Starlight pushes gas outward. Winds from the star blow the remaining dust away. The disk may dissipate over a few million years or over tens of millions. When the disk fades, planet formation slows dramatically. Without dust and gas, planets can no longer grow by accumulation. The planetary system enters a new stage, dynamical shaping. Protoplanets interact gravitationally. Their orbits shift. Some collide, some merge. Some are ejected into interstellar space. This stage can be calm or chaotic, depending on the spacing and mass of the worlds. Earth likely formed from dozens of protoplanet collisions. These impacts were not instantaneous explosions. They were slow restructurings of rocky worlds. One collision may have formed Earth's moon. Debris from the impact settled into orbit and gathered into a companion world. Other planets may form moons through capture or co-formation. Some worlds remain alone. The atmospheres of planets. Planets develop atmospheres through three methods. 1. Accretion from the disk. Gas surrounding the planet is drawn inward. 2. Outgassing from the interior. Volcanic activity releases gases stored in rock. 3. Delivery by comets and icy bodies. Impacts bring water and volatile compounds. Not every planet retains an atmosphere. Gravity must be strong enough. Temperature must be low enough. Stellar winds must not strip the gases away. This is why Mars lost most of its atmosphere, and why the Moon has none. The presence or absence of an atmosphere determines temperature stability, surface pressure, weather, the possibility of liquid water. These conditions influence whether chemistry can evolve into life. The places where life may begin. Life does not require identical conditions to Earth. It requires stable environments where complex molecules can assemble and persist. Such environments include oceans under planetary atmospheres, subsurface oceans beneath ice, e.g. Europa and Enceladus, warm regions near hydrothermal vents, protected underground layers shielded from radiation. Water is not rare in the universe. It is one of the most common molecules in interstellar space. Sphere X will search for water signatures in disks and clouds across the galaxy. By mapping the abundance of water-bearing molecules, Sphere X will help determine how common habitable conditions may be. It will not look for life directly, but it will map the foundations of habitability, the conditions that allow worlds to form, the chemistry that allows oceans to exist, the environments where stability endures long enough for complexity to arise. The universe as a planet-making machine. Planet formation is not rare. It is universal. Wherever stars form, disks form. Wherever disks form, dust gathers. Wherever dust gathers, planets eventually appear. The galaxy contains billions of planetary systems. Many are older than ours. Many are younger. Some are calm. Some are chaotic. Some contain worlds that may have oceans, mountains, and changing skies. The formation of planets is not a special event. It is the natural consequence of time, motion, and matter. Every point of starlight in the night sky may host worlds orbiting quietly around it. Not all worlds are inhabited. Not all worlds are habitable. But the potential is everywhere. And SphereX will map the ingredients of these worlds across the sky, across time, across space. Worlds of ice, worlds of fire. The diversity of planets. Planets are not uniform. They are not limited to the forms familiar to us from our own solar system. The universe creates worlds in a wide range of environments, temperatures, compositions, pressures, and orbital arrangements. Every planetary system is a unique expression of physical laws unfolding over time. The diversity of planets is not a variation from a standard model. It is the natural result of planetary formation being influenced by many conditions simultaneously. Small changes in temperature, chemical composition, or orbital distance can lead to worlds that differ dramatically from one another. To understand the diversity of planets, it is useful to begin with the two broad categories that astronomers use to describe them. Terrestrial planets, solid rocky worlds with surfaces. Giant planets, large planets composed mostly of gas or ices. But these categories are only the beginning. Within each category, there are variations so great that each world is its own environment, its own world story. Rocky worlds. Rocky planets are composed primarily of iron, silicon, oxygen, magnesium, and other elements that remain solid at high temperatures. These planets form in the warmer regions of a protoplanetary disk, closer to the star, where ice cannot exist as a solid. Examples from our own solar system include Mercury, small, iron-rich, with almost no atmosphere. Venus, similar in size to Earth, but covered by dense clouds of carbon dioxide. Earth, with oceans, plate tectonics, and a stable atmosphere. Mars, cold, dry, with a thin atmosphere and records of ancient water. Each of these worlds formed from similar materials, yet they are very different. Why? The answer lies in the amount of atmosphere retained, the amount of water available, geological activity, distance from the sun, interactions with other bodies. These factors are subtle, but their effects accumulate over billions of years. Earth retains water because its distance from the sun allows temperatures where liquid water can persist. Mars lost most of its atmosphere because its gravity was too weak to hold it. Venus experienced a runaway greenhouse effect, trapping heat and raising its surface temperature to over 450 degrees C. Small differences led to vastly different outcomes. Throughout the galaxy, rocky planets likely display similar diversity. Some may be temperate and stable. Others may be volcanic and molten. Others may be frozen and silent. Rocky worlds are not rare. They are expected to be common. SphereX will study the dust that forms rocky worlds, mapping where silicate grains, carbon compounds, and metal-rich minerals accumulate. This will help determine how frequently rocky planets form and in what environments. Ocean worlds and water-rich planets. Some planets form beyond the snow line, the distance in a planetary system where temperatures are low enough for water ice to persist. In these regions, icy grains accumulate rapidly. Planets formed here contain large amounts of water, sometimes far more than Earth. Some of these worlds may be covered entirely in global oceans. Not shallow seas, but oceans extending hundreds of kilometers deep, pressurized by gravity, layered over high-pressure ice or rock. Such worlds are sometimes called water worlds or hydrospheres. On Earth, oceans cover only the surface. On these worlds, oceans may form the majority of the planet's mass. Whether these oceans support chemistry, circulation, and energy gradients, conditions associated with life, depends on heat flow, dissolved materials, and the presence of stable atmospheres. SphereX's survey of water in interstellar clouds will help reveal how common the initial conditions for such worlds are. Water, it appears, is not rare. The forms it takes vary widely. Gas giants. Gas giants form in the outer regions of planetary systems, where ice and rock cores can grow large enough to attract massive envelopes of hydrogen and helium gas from the protoplanetary disk. The gas giants we know best are Jupiter, Saturn. Their atmospheres contain swirling bands, storms, and complex cloud layers composed of ammonia, methane, and water vapor. Their interiors are composed of compressed gases and high-pressure fluids, transitioning into metallic hydrogen deep within. Gas giants do not have solid surfaces. Descending into their atmospheres means encountering increasing pressure and density until the distinction between air and liquid disappears. Gas giants often have complex systems of moons. Some of the most promising environments for life in our solar system exist not on planets, but on moons orbiting gas giants. Examples include Europa, with a global ocean beneath an icy crust; Enceladus, which releases plumes of water vapor from interior seas; Titan, with lakes of liquid methane and thick atmosphere. SphereX will not directly observe individual moons, but it will map organic molecules in molecular clouds, revealing how common the ingredients for such worlds are. Gas giants are not unusual. They may exist in half or more of planetary systems. But giant planets also influence the orbits of smaller worlds. Their gravity can protect inner planets from impacts, destabilize orbits and cause collisions, migrate inward, reshaping systems completely. The architecture of a planetary system is shaped heavily by its giant planets. Ice giants. Ice giants contain large amounts of water, ammonia, and methane in forms not found on Earth. Our solar system's ice giants, Uranus and Neptune, are colder and smaller than Jupiter and Saturn, but no less complex. Their atmospheres contain high clouds, flowing bands, and seasonal weather cycles that unfold over decades. Their interiors are rich in water-like fluids at pressures millions of times greater than Earth's oceans. Their existence suggests that the universe creates not just worlds of rock and gas, but worlds dominated by supercritical fluids, substances that are neither solid, liquid, nor kadits in familiar terms. These planets may be among the most common in the galaxy. Super-Earths and mini-Neptunes. Many planetary systems contain planets larger than Earth, but smaller than Neptune. These worlds have no counterparts in our solar system. They are common elsewhere. Super-Earths. Rocky planets larger than Earth. Mini-Neptunes. Planets with thick gas envelopes, but smaller than Neptune. These planets are detected frequently in exoplanet surveys. They indicate that our solar system may not be typical. Super-Earths may have strong gravity, thick atmospheres, deep oceans, intense tectonic cycles. Mini-Neptunes may have layers of water vapor, icy or fluid interiors. Extended atmospheres shaped by starlight. SphereX will map water vapor and carbon compounds that help determine how such planets form. Hot worlds and cold worlds. Planets close to their stars are hot. Their surfaces may be molten. They may be tidally locked, with one side in permanent day and the other in permanent darkness. Their atmospheres may evaporate into space. Planets far from their stars are cold. Their surfaces may be frozen solid. Their atmospheres may collapse into ice. Their oceans, if they exist, may hide beneath kilometers of frozen shells. Temperature defines chemistry. Chemistry defines habitability. The diversity of planets is the diversity of environments where matter can arrange itself. Silent worlds and active worlds. Some planets are geologically active. Volcanoes reshape their surfaces. Tectonic plates move. Heat circulates from the interior. Some planets are inactive. Their surfaces do not change. Crater scars remain for billions of years. The presence or absence of geological activity depends on planetary mass, heat retained from formation, radioactive decay in the interior, tidal forces from nearby bodies. Geology influences atmosphere. Atmosphere influences temperature. Temperature influences oceans. Oceans influence chemistry. Every layer influences every other. The diversity of worlds is the rule, not the exception. The universe is not biased toward familiar forms. It produces every variation allowed by physical laws. The result is a cosmos full of rocky worlds with thin skies, ocean planets with deep blue shells, moons with hidden seas, giants of swirling storms, frozen spheres drifting in darkness, worlds warmed from within, worlds shaped by tidal forces, worlds quiet, still, silent. Many of these worlds may remain unseen forever. They orbit in dark regions of space, glowing only with the faint warmth of their stars. Yet they exist, and SphereX will help map the conditions that create them. By studying dust composition, ice distribution, molecule abundance, star-forming environments, it will help reveal where worlds of each type are likely to form. The diversity of planets reflects the diversity of the environments that shape them. There is no single way a world must be. There are only possibilities. And the universe explores all of them. The quiet chemistry of space, molecules between stars. Between the stars, space is not empty. It appears dark, silent, and vacant to the eye. But this is an illusion created by distance and scale. In reality, the space between stars contains vast clouds of gas, molecules, dust grains, and organic compounds, drifting slowly through the galaxy. These materials are thinly spread, too diffuse to form visible structures unless concentrated. But they are present everywhere. This interstellar material is not static. It moves, gathers, disperses, and reforms. It is part of a continuous cycle linking stars to planets, planets to chemistry, and chemistry to the potential for life. The quiet chemistry of space unfolds in three primary regions. 1. Diffuse interstellar clouds. 2. Dense molecular clouds. 3. Cold nerds, dust-rich star-forming regions. Each region supports different chemical environments, temperatures, and reactions. Understanding these environments is necessary to understand how stars form, how planets form, and how the ingredients of life emerge. SphereX will map the chemistry of these regions across the entire sky. Not one cloud, not one region, but all of them together, forming the chemical structure of the galaxy. Diffuse clouds, the gentle background of the galaxy. Diffuse clouds are large, extended regions of gas and dust that drift between stars. They are called diffuse because the material within them is not dense. A cubic centimeter of diffuse cloud may contain only a few atoms. To compare, a cubic centimeter of air on Earth contains roughly 10,000 molecules. In contrast, the same volume in a diffuse cloud might contain 10, and yet these clouds stretch across hundreds of light years, filling a significant portion of the galaxy's volume. Diffuse clouds contain primarily hydrogen gas, small amounts of helium, trace amounts of heavier elements and simple molecules, tiny grains of dust composed of carbon and silicates. Light from nearby stars passes through these clouds. The dust scatters blue wavelengths more strongly than red wavelengths, causing distant stars viewed through these clouds to appear reddened. This effect is called interstellar reddening, and it reveals the presence of dust. Sphere-X will measure this reddening across the sky. By doing so, it will map the distribution of dust in the galaxy, dust that influences planet formation and the chemistry of star-forming regions. Diffuse clouds are chemically simple, but they are not chemically inactive. Atoms in these clouds occasionally collide. When they do, bonds form. Simple molecules appear, such as molecular hydrogen, H2, carbon monoxide, CO, ammonia, NH3. These molecules drift freely, slowly accumulating. Eventually, some regions of diffuse clouds become dense enough for further chemistry to occur. They begin to contract. Dense molecular clouds. The hidden laboratory of the galaxy. Dense molecular clouds are colder and heavier than diffuse clouds. Temperatures in these regions drop to 10 to 20 Kelvin, only a few degrees above absolute zero. At these temperatures, molecular motion is extremely slow. Gas in these clouds is shielded from starlight by thick layers of dust. The darkness protects molecules from being broken apart by ultraviolet radiation. This allows complex chemistry to take place. Inside these clouds, molecules form on the surfaces of dust grains. Dust grains act as chemical platforms. Atoms stick to their surfaces. They move slowly across the grain. They meet. They bond. This process creates molecules such as water, H2O, methanol, CH3OH, carbon dioxide, CO2, formaldehyde, H2CO, hydrogen cyanide, HCN. These molecules accumulate into icy coatings around dust grains. The dust grains now carry frozen chemical libraries. Some of these grains will eventually become part of planets. The chemistry formed here is not rapid. It is measured in thousands of years for even simple molecules to accumulate. But time is plentiful in molecular clouds. These clouds can exist for tens of millions of years. They are quiet. They are patient. They are precise. Sphere-X will observe the infrared absorption features of molecules in these clouds. Each molecule absorbs specific wavelengths of light. By analyzing these spectral patterns, Sphere-X will map where water ice is concentrated, where organic molecules gather, where oxygen and carbon-rich materials accumulate. This map will reveal the chemical landscape from which planetary systems emerge. Star-forming regions. Heat, light, and chemical release. Within dense molecular clouds, some regions become gravitationally unstable and begin to collapse. These regions form protostars. As a protostar forms, heat increases. The surrounding dust warms. The icy coatings of dust grains begin to evaporate. This releases water, carbon compounds, and other molecules back into gas form. The warm environment around protostars becomes a dense chemical environment. Chemical reactions accelerate. Molecules collide more frequently. Complexity increases. Some of the molecules formed in these regions include ethanol, C2H5OH, acetaldehyde, CH3CHO, formamide, NH2CHO, polycyclic aromatic hydrocarbons, PHs. These are not random molecules. They are prebiotic molecules, molecules associated with the chemistry of life. This does not mean life is present, but it means the chemical foundations for life are widespread. When dust grains fall into forming planets, these complex molecules may be delivered to young planetary surfaces. On Earth, it is believed that comets and asteroids delivered a significant portion of the water and organics that contributed to early oceans and prebiotic chemistry. The chemistry of space becomes the chemistry of oceans. The chemistry of oceans becomes the chemistry of cells. The chemistry of cells becomes the chemistry of thought. The connection is continuous. Spherics will map the spectral signatures of these molecules across star-forming regions. This survey will reveal how common prebiotic chemistry is, not in one system, but across the entire galaxy. Organic molecules in the interstellar medium. Organic molecules are not rare in space. More than 200 distinct molecular species have been detected in interstellar clouds. These molecules include sugars such as glycolaldehyde, amino precursors such as aminoethanols, ring-shaped organic compounds, long carbon chains. The chemistry of space is rich. The molecules form slowly, but time is abundant. They drift quietly, but distances are vast. They accumulate gently, but their influence is profound. Spherics will identify where organic molecules are present in large-scale structures. It will not detect individual molecules one by one, but it will observe the broad chemical signatures of regions rich in organics. This will produce the first all-sky chemical atlas of the Milky Way, an atlas that reveals where life-building molecules are common, where they are scarce, how they are distributed across star-forming clouds. This is not a search for life. It is the search for the materials from which life can emerge, a search for potential. Dust, the carriers of chemistry. Dust in space is not like dust on Earth. It is composed of tiny, complex grains of minerals and carbon compounds. Dust plays three essential roles. 1. It shields gas and molecules from destructive light. 2. It acts as a surface where molecules can form. 3. It is the solid foundation of planets. Without dust, stars could still form, but planets could not. Dust is the seed of solid worlds. Spherics will map the properties of dust grains by observing how they absorb and emit infrared light. This will reveal dust size distribution, dust composition, temperature variations, regions where dust is growing into pebbles. This is the earliest stage of planet formation. The process is slow, there is no rush. But dust is persistent. Dust becomes grains. Grains become pebbles. Pebbles become stones. Stones become worlds. Every planet begins as dust drifting in space. The quiet chemistry continues. The interstellar medium is a network of slow reactions. No urgency, no explosion, no rush. Just time, motion, temperature, gravity, light acting gently, continuously. Spherics will observe this chemistry not in a single region, but everywhere. The quiet chemistry of space forms the background of the galaxy. It fills the space between stars. It shapes the environments where stars and planets arise. It provides the raw materials for worlds. What happens in the dark, cold, quiet clouds between stars determines what worlds can become. The universe builds slowly, but it builds with consistency, with precision, with patience. The chemistry continues. The long future. How the universe continues to change. The universe is not static. It has never been still. From the moment of its beginning, it has been expanding, cooling, and unfolding into new structures. The stars that shine today did not always exist, and the stars that will shine in the future will not be the same as those we see now. The galaxies we observe are moving, drifting slowly apart. carried by the fabric of space itself. This expansion is not explosive, not chaotic, but gentle and continuous, occurring over billions of years, almost unnoticeable across a single human lifetime. Yet, it accumulates. Even now, galaxies separated by great distances are receding from one another faster than the speed of light, not because they are moving through space, but because space itself is stretching. As the universe expands, its average temperature continues to decrease. In the early universe, everything was hot, dense, and bright. Now, most of space is extremely cold, only a few degrees above absolute zero. Light travels through these dark regions, passing ancient dust, drifting through vast distances with little to disturb it. In this cold and quiet environment, galaxies continue to evolve. Stars are born in molecular clouds, age slowly, and eventually die. Some explode, some fade, some collapse. But no star remains unchanged forever. Our own sun is about halfway through its life. It burns steadily now, releasing energy through nuclear fusion in its core. There will come a time, billions of years from now, when its hydrogen fuel becomes depleted. When that happens, the balance between gravity pulling inward and pressure pushing outward will shift. The core will contract and heat up, while the outer layers expand outward. The sun will grow into a red giant, stretching its atmosphere outward until it engulfs the inner planets. Whether Earth will be consumed or merely scorched is uncertain. But even if Earth remains physically intact, it will no longer be habitable at the surface. Oceans will evaporate, the atmosphere will escape, and the surface will become barren and silent. After the red giant phase, the sun will shed its outer layers into space, forming a planetary nebula, an expanding shell of glowing gas. The core that remains will become a white dwarf, a dense, hot remnant roughly the size of Earth, but with the mass of the sun. It will shine for billions of years as it slowly cools. Eventually, it will fade into a cold, dark object known as a black dwarf. This final state will not arrive for a very long time, longer than the universe has existed so far. So long that time itself seems to stretch beyond comprehension. Other stars will follow similar paths, but some stars are much more massive than the sun. Their cores burn brighter and faster. They consume their fuel more quickly. Their lifespans are shorter, sometimes only millions of years instead of billions. When they reach the end of their lives, they collapse and explode as supernovae. These explosions scatter elements into space, seeding the galaxy with heavy elements such as iron, nickel, copper, gold, and uranium, materials forged in the extreme temperatures of stellar cores. These elements combine with gas and dust in interstellar clouds. They are incorporated into new stars, new planets, and eventually living systems. The iron in human blood was once created in the core of a star. The calcium in bones, the oxygen in the air, the carbon that forms the foundation of organic chemistry. These too were created through the life cycles of stars. The universe builds itself from recycled material. Nothing is wasted. Everything cycles. The galaxy itself will change over time. The Milky Way is moving through space, slowly spiraling. It rotates once every 230 million years, carrying stars in wide orbits around its center. The sun drifts along with its planetary system, tracing a slow arc through the galactic disk. The galaxy also drifts toward Andromeda, another spiral galaxy. In approximately 4 billion years, the two galaxies will begin to merge. The merger will not be explosive or violent in the way we might imagine. Stars are far apart, so they will not collide directly. Instead, gravity will stretch their shapes, draw out long streams of stars and gas, and eventually reshape the galaxies into a new, larger one. Planetary systems may be disturbed. Some stars will be thrown into new orbits. Some may be ejected into intergalactic space, drifting alone with their planets. But the process will occur over hundreds of millions of years, almost imperceptibly slow on the scale of a single lifetime. The expansion of the universe, however, will continue. Space will stretch, and dark energy will drive galaxies farther apart. Over time, galaxies not bound by gravity will drift beyond the horizon of visibility. Light traveling from them will no longer reach us. The sky will slowly grow emptier. The distant galaxies we see today will disappear from view. Star formation will slow, as the gas required to form new stars becomes scarce. Over trillions of years, stars will burn out one by one, leaving behind cold remnants. The universe will become dark. This far future is often called the era of degenerate matter, when white dwarfs, neutron stars, and black holes dominate. Black holes will gradually grow as they draw in surrounding material. Over extremely long timescales, even black holes will evaporate through Hawking radiation. They will release energy slowly until they eventually vanish. The universe will approach a state of near-perfect uniformity and low energy, a state of quiet stillness. But reaching this state is not the same as ending. The universe does not conclude in a moment. It does not switch off or collapse. It approaches equilibrium slowly, gracefully, patiently. It continues to change, even when change becomes increasingly subtle. Time stretches on, unhurried. And in the present, long before this distant future, the universe is still full of light, structure, motion, and creation. Stars are forming now. Planets are forming now. Molecular clouds are gathering material. Gravity continues its work. Chemistry continues in dark places. Atmospheric cycles unfold on distant worlds. Oceans rise and fall under alien skies. Moons shift in silent orbits. The universe is not static. It is alive in motion. Sphere-X will observe the universe as it is now, during this active phase of star and planet formation. It will map the distribution of water molecules in molecular clouds. It will examine the chemistry surrounding newborn stars. It will trace dust across the galaxy. It will observe the structure of large-scale cosmic patterns. It will create a record of the present, a snapshot of the universe, while it is still full of light and movement. The purpose of Sphere-X is not to look backward to the beginning or forward to the end, but to map the ongoing universe. The universe in the process of becoming. The sky is not finished. The galaxy is not finished. Planet formation is not finished. Chemistry is not finished. Nothing has stopped. Everything is still unfolding. The universe continues, quietly and steadily, and we observe it, not to control it, but to understand our place within it, to see that we are part of its unfolding, to recognize that the atoms that form the body were once part of stars, were once part of clouds, were once drifting in interstellar darkness. The story of the universe is not separate from the story of life. They are the same story, unfolding across time, shaped by gravity, motion, temperature, and chance. The future of the universe is long and calm. Not abrupt, not dramatic, just gradual transition, slow change, and the quiet passage of time. The cosmos does not rush. It unfolds. And so, we drift here, in the quiet of the universe, suspended between stars and time. The journey has carried us from the hearts of collapsing clouds to the birth of new suns, from dust gathering patiently into planets to oceans hidden beneath ice, from the inner fire of living worlds to the silent chemistry unfolding in the darkness between them. Each part of the cosmos moves at its own pace, unhurried, guided by gravity and temperature and the gentle passage of time. There are no sudden beginnings, no final endings, only transitions that unfold across spans far larger than any human life. Yet we are connected to all of it. The iron in our blood was formed in stars that burned long before the Earth existed. The oxygen we breathe was released by life that grew slowly in ancient oceans. The carbon in every cell once drifted through the galaxy as interstellar dust. The atoms that form our thoughts were shaped in thermonuclear cores and scattered across space by the collapse of worlds. We are not separate from the universe. We are expressions of it, carried forward, arranged, recombined, alive for a time, and then returned to the wider cycle. The universe does not look at us from a distance. It continues through us. Even now, above us, stars rise and set in patterns millions of years old. New stars are forming in distant clouds, quietly igniting their own futures. Planets are gathering themselves in slow spirals around newborn suns. Oceans are filling with minerals in motion. Moons turn in the deep silence of their orbits. Light travels outward in every direction, carrying information, carrying memory, traveling farther than worlds will ever move. The universe continues to breathe, if breathing can be understood as expansion, motion, and unfolding. There is no need to hold any of this tightly. It is too large to be possessed. The mind can simply rest in the knowledge that everything changes, and yet everything is part of a continuity that began long before us and will continue long after. We do not need to solve the cosmos or define it. We only need to allow ourselves to feel the steadiness of it, the quiet rhythm of expansion, the slow dance of gravity, the gentle cooling of time. For now, there is nothing to do, no direction to move, no timeline to meet. Only the quiet presence of being here in this moment, carried by breath, resting in the vast calm of the universe. The stars will continue their cycles. The galaxies will continue their motion. The chemistry of life will continue in its own unfolding. And you may simply rest, knowing that you are part of that same unfolding, part of that same continuity, part of the same ancient and endless peace. Let the mind settle. Let thought drift. The universe will continue, and you may rest.